Hi everybody, my name is Robert Coy. I'm a senior scientist working at TNO and I'm also part-time affiliated with the Delft University of Technology as a professor. Unfortunately, I could not make it here today to join this wonderful workshop, but I find it such an important workshop that I decided to make a presentation, make a video of it and also share it with you in this way. So the title of my talk is Robust Network Design, and in fact, the objects that I'm interested in to study, to do my research, are simply networks. So that's a collection of nodes that can be connected by links. And this is just a simple example that you see. Now, my main interest lies in the so-called robustness of these networks. And the robustness I define as the extent to which these networks are able to cope with perturbations imposed on it. Now, these perturbations, you can think of failures. They can be incidental, can be mistakes made by people, but they can also be deliberate when you think, for instance, of attacks. It could be terrorist attacks, could also be cyber attacks, things like that. Now, what I'm interested in mostly is to quantify the robustness, so to quantify the extent to which networks are able to cope with perturbations by using network science, by using properties of the network, and by extracting information from the network by using analytic methods. Now, the reason that this is an important subject, in my opinion, is that society nowadays heavily depends on the proper functioning of a lot of networks. Sometimes we also call them critical infrastructures. So this is specifically the domain, these critical infrastructures, where we also apply these type of analysis. So just to give you an example of two domains where we apply the robustness analysis. First of all, it's in the field of the energy. So for instance, here you see a picture of the European power grid. And we have, with our methods from network science, we have been able to determine which links or which nodes, which generation stations are the most vulnerable in this situation. Another application domain, also very relevant, is that of telecommunication networks. Now, of course, we are here today to talk about a different critical infrastructure, that is public transportation networks. And I also did some work on a specific type of public transportation network, namely metro networks. Now, to do this, we set up a collaboration with the University of Illinois at Chicago. And we obtained data of 33 metro station networks in the world, including the metro network of the city where I'm staying right now, which is Singapore. So you see a picture of it here. And actually what we did is we compared two types of approaches to obtain the robustness of these metro networks. So the first approach, quite straightforward, is by using simulations. And here we study the loss of connectivity in case of the failure of certain stations. So here you see an example of what I mean with that. So in this case we studied the metro network of Tokyo. On the horizontal axis you see the number of nodes that we could possibly remove. And on the horizontal axis you sort of see the performance, the degradation of the connectivity of the networks, of the network as we increase the number of nodes that are removed. Now typically a performance metric that you can look at here is what is the number of nodes I have to remove before 10% of my nodes or my connectivity is lost. So that's a typical example of a robustness metric, a connectivity metric you can get from these simulations. And what we did next is also use, as I said before, methods from network science. That is to look at analytic metrics that you can compute just by looking at the topology of the network. And the one we looked at in this specific study is the so-called Kirchhoff index, which, by the way, also comes from the study of electricity networks, obviously. And then what you do is you try to correlate the results that you get from simulations and from the analytical metrics study. And in fact, for this specific study, we have been able to show a Pearson correlation in the order of 0.9. So that's pretty sound result. Now, what would I like to do within this project that we are talking about today? Well, first of all, I would like to develop more advanced robustness metrics. Now, how could you do that? For instance, so far I didn't take the traffic flows into account, and obviously they also play a role. We could also look at multimodal forms of transport. And we could also use user-generated data that might also give some extra information and also about possible decisions that may be made by the users and also have an impact, a possible impact on the robustness. Of course, the aim to have this advanced robustness metrics is to, by using them, be able to have a better design and a better operation of the public transport networks. Thank you for your attention.